turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists. This is the show where we bring you the latest breakthroughs and talk to the greatest movers and shakers from the realms of science, technology and medicine. I'm Chris Smith, and today, how engineers are attempting to tackle the climate crisis.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
The United Nations recently described climate change as the defining crisis of our time, and one that's happening even more quickly than it could possibly have predicted. The burning of fossil fuels, deforestation, industry and overpopulation have certainly all played a major part in forcing global temperatures to rise. This has ultimately led to more extreme weather events, rising sea levels and the destruction of natural habitats. Policymakers have often dragged their feet in a bid to halt these seismic changes. But, as the UN points out, we are not powerless to stop it, and science is increasingly coming up with new ways to tackle the problem. We're going to be examining some of the more innovative ways that researchers are engineering solutions to the climate crisis over the course of today's programme. And to help us out first, though, here's Mark Maslin, who's a Professor of Climate Change at UCL and also the author of How to Save Our Planet.
Last year, 2023, was the warmest year on record, hitting average of 1.48 degrees Celsius above pre-industrial levels. But even worse, if we look at the last 12 months, we have gone past the 1.5 degree target, which was set up by the Paris Agreement in 2015 by the leaders of the world. And the problem is that we haven't turned the corner. 2023 was the year when we emitted the most greenhouse gases ever in recorded history.
People often liken climate change to an oil tanker. Probably quite a difficult analogy to use, isn't it, given what's in the oil tanker? But the point being that this has a lot of momentum. And when you want to stop the tanker, you don't turn the engine off at port because you will crash. You turn it off out at sea and you aim to coast to a stopping point. So how far do we think the climate juggernaut is going to coast? Even if we do all these things now, how bad are things going to get?
We know if we stopped putting greenhouse gases into the atmosphere tomorrow, the temperature would stabilize where it is now. Great. The problem is, and I love your analogy of the oil tanker, the societies we live in have a predisposition to actually use fossil fuels because everything's built on it. The oil companies are making huge amounts of money. Countries are making tax dollars from those oil companies, and therefore people are very reticent to actually move away from this cash cow. And also, what I really like to point out to people is the International Monetary Fund monitors the amount of taxpayers' money that is subsidizing fossil fuel companies. And last year it came out about $1 trillion. That is about half the GDP of the United Kingdom. Every single year is being given straight to the oil and the gas companies to pollute our atmosphere, which we, the taxpayer, will then have to pay to fix.
The problem is that we're going to get a lot of very old people very cold in winter in countries like the UK if we don't provide them with fossil fuels because we just haven't invested, and we're not alone in this. Every country is guilty to some extent, but we haven't invested in the alternatives quickly enough, have we?
So we can shift things physically with good engineering and good policies very quickly. And the idea that the only way you can heat homes in cold countries is through gas is ridiculous when you look at Scandinavian countries where they all use heat exchangers.
Population of a Scandinavian country might be a couple of million. Population of one part of London is a couple of million. The housing stock we have in the UK is a lot of it Victorian. It's very poorly insulated and a heat pump just won't cut it. Not that the grid could cope with the demand either. So we find ourselves actually in a difficult position for multiple reasons. It's not just a question of we have to stop using gas. We've got a big headache with dealing with our ancient building stock, haven't we?
Well, for me in the UK, this is where climate change and other social issues become a win-win. We have some of the worst housing in the whole of Europe. And so, therefore, what we need is policies that say, how do we improve the housing stock? So, we actually move people in the UK from 19th century housing into 21st century housing so they are healthy and have the environment they should have in one of the richest countries in the world.
We're going to hear a bit later on about making concrete in a more environmentally kind way, but that's going to be a big headache, isn't it? Because if we have to rehouse a large proportion of the population, if that's what you're saying is the engineering challenge that confronts us, then that's a lot of cement, and that's an enormous carbon footprint.
So we have a look at cement now. If cement itself was a country, it would be the sixth largest emitter of greenhouse gases in the world. But it's also absolutely essential. So what we need to do is think about ways that we can use technology to make it less polluting. Instead of just damning things and going, do you know what, concrete, awful, we shouldn't use it. No, but we should make it better.
What about energy sources and energy transmission? There've got to be some wins there. People keep talking about, for instance, a re-evaluation of nuclear and the concept of small modular reactors, that kind of thing. Do you think that is worth considering?
So for me, energy is absolutely key to solving the climate crisis. 80% of all the world's greenhouse emissions from energy comes from fossil fuels. Interesting fact, if we stop using fossil fuels completely, 40% of all ships on our high seas would not be required. That gives you the scale of how much fossil fuel we move around and how much we burn every single year. So if you look at the engineering solutions, renewables are simpler technology, cleaner technology, and local technology. I think the key technology will be in the second half of this century, fusion. Now, fusion, the scientists have done their jobs. We have the actual scientific understanding and we've created more energy than we put in. What is now the problem is it's a massive, and I mean a massive engineering problem. How do you take the laboratory and scale it up? Now, the UK government has set aside land and money to try and build the first fusion sort of reactor in Nottingham, but it's going to take huge amounts of new engineering to actually produce that.
Mark Maslin, author of How to Save Our Planet, on why tackling climate change is chiefly an engineering problem. And indeed, across the rest of the programme, we're going to explore some of those engineering answers, which also include building superior ways to monitor climate change and our progress against stopping it. And in this regard, the UK's Advanced Research and Invention Agency, or ARIA, recently announced that it's allocating £80 million to a new programme that aims to create early warning systems for climate tipping points. These tipping points get their name because, if crossed, they can trigger abrupt and irreversible onward changes to the Earth's climate. ARIA hopes to bring together the best and the brightest scientists in the world to predict when they might happen, so we can do something about them. To find out more, I went to see Sarah Bondique, the Programme Director at ARIA and a Professor of Biomedical Physics at the University of Cambridge. What, I wanted to know first, constitute these climate tipping points?
For example, we might think about the melting of an ice sheet that would contribute significantly to sea level rise. Or we might think about the collapse of an ocean circulation that could shift the position of the jet stream, change the weather in various parts of the world, which would lead to problems with agriculture, biodiversity, impacts on food security. These things are happening on timescales that are still unfolding.
And is the purpose of the project to identify what those tipping points are? To actually make a shopping list of them so we know what to look for and therefore can size up the risk?
In our programme, we're looking at how we might understand when those tipping points would occur, over what timescales they might unfold, and what the consequences of crossing them would be. At the moment, we have a pretty good understanding of which parts of the Earth system are prone to undergoing this kind of tipping between different stable states. But what we're lacking is the ability to detect when this is coming. We know that some systems are undergoing significant changes at the moment. But the question is, do these changes commit us to, for example, the entire loss of an ice sheet? And we have two major challenges that are preventing us from getting to that point. One is the data. If we think about weather forecasting, we can do that with pretty good accuracy because we have an abundance of data. We're very good at knowing when a heat wave is coming, when a major storm is coming. If we try to think about when a tipping point is coming, often these things are in incredibly harsh environments. If we're talking about ice sheets, we're talking about extremely cold in remote places, which are very hard to make measurements in. So we have a real scarcity of data, not just on a day-to-day basis, but also long-term records going back decades or centuries. Earth is such a complex and variable system. If we want to detect these changes, then we would need to have a really long record of data from which we could detect these subtle changes that we're approaching a tipping point. The other problem is a modelling problem. We have extremely sophisticated climate models that teach us about how the climate is changing over time, how different systems interact with each other. But these are hugely computationally challenging. Despite their incredible sophistication, they don't always include all of the processes that we would need in order to describe these tipping processes, understanding how we cross tipping points. On top of that, they're very computationally expensive. Being able to calculate a trajectory for how the climate might evolve over the coming decades or centuries takes an incredible amount of computational power. As a result of that, it's also quite hard to integrate observations that we're getting every day around the world. We're setting out to try and see whether it would be possible to set up an early warning system that unites modelling and measurements and helps us to understand better when these tipping points are likely to arise.
How does this work in practice, though? Do you kind of orchestrate and bring together people who are working on this kind of problem all around the world, or are you single-handedly going to try and take on this challenge? What's it look like in practice?
I'm certainly not going to manage it single-handedly. This is really a global problem and needs global talent to come together. As a programme, we're going to coordinate scientists from across the world. We can fund companies, we can fund academics and universities. We can really reach out to people who wouldn't ordinarily have the opportunity to work together. We're particularly interested in bringing new people into the field of climate science. So I myself am not a climate scientist, I'm a medical physicist. And I've come into this field with the blank slate that ARIA has given me and the mandate to set up a programme. And together with my colleague Gemma Bale, who's co-directing the programme, we've looked at this field with fresh eyes and come up with interesting ideas that we think are really important for tackling some of these problems. And we really believe that there are a huge number of people out there with expertise in new sensing and new imaging that could come and help tackle the climate crisis.
It's really interesting that the policy has taken you in this direction. We've basically arrived at a situation where we have researchers, scientists using scientific insight, but to run a program like this and have resource behind them to fund other people to get involved, instead of relying on all those individuals to come together independently under some kind of government policy or something. That's quite an interesting and innovative way of doing things.
It's a really key part of the ARIA model is to put people first, then projects. And that starts with recruiting us as programme directors and giving us that blank slate to go out into the community and find out what are the big problems of today and how can we reach for the edge of the possible to try and tackle them. In talking to the climate science community, we really identified these gaps in observations in harsh environments and also these challenges with building up the next generation of models. And we felt that we could really push this forward if we were able to build up a programme around early warning of tipping points that integrated both of those things together. So having that scientist lens means that we can understand what some of the challenges are in building new sensors. What does it take to get a new measurement at the deepest depths of the ocean? What does it take to take a picture with a camera if you're out in the Arctic Circle, for example? Those are things that we've both worked on in our backgrounds as physicists, so we have an understanding of some of those challenges, but we've never thought about them in the context of climate science before.
Sarah Bondique, the Programme Director at ARIA and Biomedical Physics Professor at the University of Cambridge. We were hearing earlier from Mark Maslin that our infrastructure, things like our ageing housing stock and our built environment, poses a huge problem when it comes to climate change. In a bid to redress some of the problems that concrete causes, Alelia Keir, who's a materials scientist and engineer at Imperial College London, has developed a version of it that tackles one of the other major challenges that are predicted to come with climate change: altered rainfall patterns and more extreme weather. This all adds up to requiring better stewardship in the future of our water. At the moment, as cities expand and we concrete over the countryside, we render the ground below impervious to rainfall, which all hits the sewers in one giant rush and then causes flooding, and is also lost, ultimately, out to sea. The earth below is progressively deprived of water that would previously have soaked in and restocked groundwater. So Alelia's eponymous product, which has been developed with the help of UK Research and Innovation and also the Royal Academy of Engineering, is called Keircrete, and it's concrete with holes through it that allow water to run through so it can be captured and used, and also soak into the ground like a sponge, so a deluge doesn't turn into a flood.
There are a number of different challenges that the engineers are facing today, including decarbonisation, ensuring that the UK hits its national carbon targets. And also another problem is flooding. So we need to not only ensure that we reduce our carbon footprint of our flood management interventions to contribute to net zero targets, but also we need to ensure that our infrastructure are capable to cope with more extreme weather events.
Is there anything we can do about that problem of the fact that concrete is largely impervious and the water that lands on it runs straight off and goes down the drain? Is there a better way of doing that?
So one of the ways is to ensure that pavement infrastructure is permeable, is able to allow the water to go through it and to prevent that nuisance to the society, and also that water is then used in a more clever way rather than the way it is now, which just ends up into the drainage network and causes more problems down the line.
And how can we do that? Because isn't one of the major things about concrete the wonderful aspect of it that it's incredibly strong? You can put massive loads on it, but in order to achieve that, you have to have something which effectively is solid rock.
To achieve a high strength, you don't necessarily have to be completely impermeable. So what we have been trying to do is to come up with a pavement structure that essentially has a lot of channels in it that would allow that water to drain through it. So it still will have the same strength as your traditional impermeable concrete surfaces, but it has the added benefit that it has a really high permeability or drainage ability that eliminates flooding and stormwater runoff, and also improves the splash and spray related visibility issues, and it reduces weather related accidents. So it eventually enhances the societal safety.
How does it work?
So essentially, you have a formwork that has a lot of these channels inside it. So you pour your cementitious materials around that formwork, and then that gives you a concrete surface that has a lot of holes inside it. Once you have your extreme weather event, extreme rainfall, the water goes through those holes down into the ground.
I'm just picturing this in my mind. So is it effectively a mould then with lots of holes, and you put concrete into that mould, and that means that you get concrete with holes in it, which then allow the water to go vertically through the concrete layer? But because the concrete's still all connected together, it's still strong, but it's got channels in it.
That's essentially it. You're essentially picturing a solid concrete that has a lot of holes in it, as you mentioned earlier, a formwork that has all of these interconnected channels that would allow the water to go down vertically, but also the material has a really high strength that can sustain the loads of an aircraft or vehicular loads or pedestrian loads or cyclist loads.
And when you say you can capture and therefore repurpose the water that goes down those holes, is that because there's some way or some system of collecting what's come through the holes underneath? So would you lay the concrete on something that's capable of acting as a conduit for that water, which is how you grab it?
Yes. So essentially, the pavement surfaces are typically built on what we call a porous substructure. So we're talking about just stones. And the water would go through those stones, and then it goes into what is called a storage tank. So this storage tank would, first of all, delay the water and prevent the water from going into the drainage network and causing flooding downstream. But also that water that is within that tank could be used for irrigation purposes, or it could even depending on the area that is built in, it could go into the ground and recharge the groundwater table.
What about in countries like ours in winter where it's incredibly cold and you can get frost? Because one of the biggest problems with concrete and water is frost shattering.
So the benefit of the system that we have developed is that it's very efficient in absorbing water as quickly as possible. So we've had a number of field trials and also laboratory testing where we exposed this solution into extreme temperature, so extreme heat, extreme like freezing temperature, and then heating it. And we've shown that it actually doesn't allow the frost built up on the top surface because it's has a lot of holes, is very efficient in allowing the water to go through it as quickly as possible and not leading to that layer of frost to be built up on the surface.
And the cost implication, because the one thing that developers are always going to look at is the bottom line, because you're using less concrete because you've got the holes in the way, does that actually translate into a saving?
So when you look at the cost, we need to look at the whole life cost of the pavement structure. So the initial cost in terms of the labor cost is similar to the traditional pavement surfaces. But when you look at the whole life cost, it's actually much cheaper than the traditional pavement surfaces because not only you're reducing the challenges that you would be facing with the impermeable surfaces because of this rainfall and runoff issues, but you're also reusing that water. And it's a pavement that has much more reduced maintenance in comparison to traditional pavement surfaces. So essentially, you're saving on that front. And as you said, you're also saving in terms of material because you're using less material in comparison to the traditional surfaces. So if you consider the whole life of the pavement structure, it has lower cost than the traditional surfaces.
And importantly, in the built environment, it also seems to produce a lot less noise than traditional concrete when vehicles run over it, which is a very nice added bonus. That was Alelia Keir at Imperial College London on Keircrete.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
And you're on The Naked Scientists, with me, Chris Smith. Still to come, the Cambridge scientists who are ultimately trying to refreeze the Arctic. But first, we're going to explore the solutions that chemists are offering up in a bid to tackle climate change. Researchers in London recently successfully replicated the crucial part of a plant enzyme that drives the process of photosynthesis, which is what captures carbon from the atmosphere for plants. The work could open up new avenues to trap CO2 and pull carbon dioxide back out of the atmosphere in the future. To find out more, we put in a call to Dan Wilson from University College London.
Nature has been dealing with carbon dioxide for millennia now. So what it has done is evolved to have molecular machines, which we call enzymes. There's a variety of enzymes which take carbon dioxide and convert them into cellular carbon. And this can be useful because we need to be able to build the cells and biomass and sugars and things like that for energy, and also so that we can grow as organisms.
Effectively, that's photosynthesis, isn't it? It's using the energy in the sun to grab carbon dioxide from the atmosphere and turn it into a chemical form that feeds everybody.
That is exactly right. The key thing is that you need to have a carbon source and an energy source. So photosynthesis is famous because it uses light, but you could also use things like thermal energy as well.
And that reaction centres on enzymes, which effectively drive it. How are you taking your lead from that process or attempting to build on it?
What we do is we look at data from the enzymes, in particular what's known as X-ray crystallographic structures. So these are 3D images of really large molecules, and what they do is they provide snapshots into what these enzymes actually look like. So we can take these photographs and see where the reaction actually happens. In this case, what we want to do is figure out how an enzyme takes CO2 and then through various transformations along the way, converts it into, in our case, acetyl coenzyme A, which is just this form of biomass.
The aspiration being that if you can produce your own artificial leaf, I suppose you could say, that you can make artificial photosynthesis, not only solve the carbon dioxide problem, but produce some useful energy molecules in the process.
Exactly that. You could have some sort of material where you put it inside sunlight, it then takes CO2 and converts it into something else that is quite useful to us as chemists. How the machinery that we can see actually performs the transformations is still very much a mystery. So a lot of the steps along the way where we've captured, say, CO2 and we've started to transform it into something else only exist for very, very short periods of time. And we really struggle to observe what's going on at those points. So what we're trying to do is figure out reasonable mechanisms for how you go from CO2 to something like cellular carbon. What we've learned is you can strip back the enzyme quite significantly. So rather than looking at quite a large molecular structure, you can simplify it to just look at a small section, which we know as the active site. So that is the part where the reactivity is happening. By truncating it just to the bare bones, so just a few of the required structural features, we can still build functioning models of the enzyme itself. What that would mean is that we can, in future, build simple molecules which perform similar functions to these large enzymes, and then hopefully we can employ them to do these sorts of transformations.
So now you've understood what the key ingredients facilitating this chemical process of turning carbon dioxide into more complicated molecules is. How good is your system? How much CO2 will it convert by when? Is it a rival for what, say, a tree is doing?
Definitely not even close to what a tree can do. Our catalysts are currently quite early stage in development, so that they're not actually industrially ready yet. They were having a lot of trouble with things like air sensitivity because they're very sensitive to oxygen, which means they're not very useful for practical applications yet.
So it's a start, and you've got to start somewhere. So say you get this working, and you get it working well, you will have a recipe for molecules which, if you make them, can grab CO2 and turn it into useful stuff. So what's the application then? How is that actually deployed industrially or technologically? How would you use what you aim to create?
The most useful product to come out of a reaction would be methanol and methanol derivatives. So methanol is useful in that it's a liquid, so it's much easier to store than CO2. It also can be used as a solvent in a lot of chemical transformations, and quite importantly, it can also be burnt as a fuel. So there's a lot of interest in the field right now of developing catalysts which take CO2 and selectively and efficiently convert them into methanol.
And you can see the road ahead to be able to do that.
So that's a tough question. Yes, we now have a lot of catalysts that can take CO2 and convert it into methanol. The difficulty is where you get the hydrogen atoms from for that reaction. So in an ideal case, what you'd have is some sort of fuel cell type device where you have CO2 or carbon dioxide reduction happening in the presence of water oxidation, and the water oxidation would provide protons for the resultant methanol. However, we don't have any technologies which can do both of those things at once with sunlight as the energy source just yet. In the next few years, that sort of technological development is on the cards.
And will the molecules that you're making at the moment, will they be easy to make? Is this going to be so difficult to make that it's just uneconomically viable? Or is this going to be relatively easy to put it on the shelf?
What we are trying to learn from the molecules is what structural features are necessary for reactivity. So it's both structural and other features, things like what transition metal is in there, what the geometry is, and things like that. So what we're hoping is that when we learn which of these features is actually important, we can take that understanding and apply it to developing all sorts of different catalysts. So it's not so much about our specific molecules, it's more about understanding principles that will help us.
Dan Wilson there from University College London, and that study was recently published in the Journal of the American Chemical Society. Finally today, we're going to tackle one of the more left-field attempts to tackle climate change. Sean Fitzgerald from the University of Cambridge's Centre for Climate Repair is behind one such project with aspirations to refreeze the Arctic and preserve the ice there, buying us time while we come up with other ways to stabilise the climate.
Every scenario considered by the IPCC in their most recent report considers a large suite of measures on emissions reduction complemented by greenhouse gas removal. And while some of those actually do see us below 1.5 degrees centigrade by the end of the century, the sad fact is that every scenario that they now consider sees us exceeding 1.5 degrees centigrade in the interim period. And we're greatly concerned about the changes which are going to be unleashed on the planet. In other words, the loss of ice on Greenland, the loss of ice on Antarctica. And therefore, what we're trying to do is equip ourselves with knowledge so that a society can make an informed decision as to whether these engineering solutions could be put in place in order to buy us more time to get greenhouse gas levels down whilst keeping the ice on Antarctica and the ice on Greenland, for example.
In a nutshell, are you basically advocating for refreezing Greenland?
Well, I'm certainly advocating for doing everything that we can to keep the ice on Greenland and the ice on Antarctica.
Greenland has lost billions of tons of water, provoking some of the sea level rise that you've just been referring to. So this is not a small, trivial thing to just keep the ice there. How do you anticipate trying to do this?
In general terms, there are two big factors that determine the temperature of the Earth and therefore the rate of, for example, melting of ice on Greenland. The first is the amount of radiation coming in from the sun. And what we can do is look at measures to reduce the amount of the sun's radiation that actually gets down to the Earth's surface. And those approaches are termed solar radiation modification. They can include things, for example, by emulating the effects of volcanoes. Volcanoes such as Mount Pinatubo, when it erupted, it spewed about 20 million tons of sulfur dioxide into the stratosphere. That then reacted with water vapor to form little droplets of sulfuric acid. And those little droplets of sulfuric acid were of the right length scale, diameter, that they were able to reflect a very small portion of the sun's radiation. And the second big idea is whether you can actually get more of the Earth to radiate heat out at night and actually help, therefore, in terms of the overall radiation balance over either a year or certainly over a day.
Let's start with the first of those ideas. You've presumably done more than just back-of-the-envelope calculations on what this is going to take. So hit me with the hard facts. How much cloud forcing or seeding have we got to do in order to preserve the Arctic?
Something like 10 million tons per year of sulfur dioxide being injected into the stratosphere could indeed cool the Earth by circa 1 degree Kelvin. And that's a really useful benchmark. Now, what does that really look like? In other words, how would you get 10 million tons of sulfur dioxide up into the stratosphere from an engineering deliverability point of view? That's thousands of flights of aircraft a day in order to get to that sort of kind of delivery schedule.
The other idea you proposed was to try to get the Earth to get rid of more heat. Tell us a bit more about that, because I haven't heard anyone say anything about that.
Well, one of the things that we are looking at is something called sea ice thickening. The first effect of this is that how can you get more sea ice to grow in the Arctic winter? And the reason why you might want to do that and get the ice to be thicker is that the ice will actually then last longer over the Arctic summer and therefore reflect more of the sun's radiation as it impacts on that ice in the Arctic summer. But let's just think about what's going on in the Arctic winter. What you're really doing is if you're getting more ice to form in the Arctic winter, given there's more freezing, then the latent heat of solidification has got to go somewhere. And ultimately what you're doing then is actually getting that latent heat of solidification, freezing, to be radiated out to space in the Arctic winter. And the way that you do that potentially is by pumping seawater, not very far, but pumping it up from under the ice to on top of the ice and getting the freezing process to then occur on top of the ice. The top surface of the ice in the winter is, let's say minus 20 degrees centigrade. If you've pumped the water on top of the surface, then by definition, it's liquid water. And the temperature is no longer minus 20 degrees centigrade. The temperature is, let's say, minus 1.5 degrees centigrade. But that difference in temperature actually results in an increase in the rate at which heat is being radiated out to space in the Arctic winter.
And how much energy have we got to expend pumping water in order to get a net cooling effect?
There are two flavors of this particular problem that we're looking at. The first is where you're pumping seawater on top of the sea ice in order to make that new sea ice on top of existing sea ice. The second idea that we're looking at is where, in fact, all you're doing is pumping enough water on top of the sea ice to consolidate any snow that then falls naturally on the sea ice. And if you can turn that snow into solid ice, snow is a ridiculously good insulator, and therefore you've increased the conductivity of the overall matrix. And what that means is that just pumping enough water to convert the snow into solid ice, you've increased the rate at which new sea ice can form naturally. And that will require far less pumping, far less energy for a given amount of new sea ice that can accumulate naturally. That one excites me greatly, but we're looking at both of these approaches, Chris.
And how does this go down when you present these ideas, both at home but also when you go to conferences or international meetings and so on, and you talk to the community about these ideas? How does this go down with fellow engineers, climate scientists, etc.?
I get a mixed response, to be quite straight with you. Those who have an open mind as to, look, we're not in a good place, but we need to be learning more so that society can make more informed decisions, are really eager to help. Whereas there are those who think these sorts of ideas are a distraction. And whilst I accept that that is a viewpoint, I don't agree that that is the cause of the lack of progress that we have made on emissions reduction to date. When we go and talk to people about why we've been making such paltry progress on emissions reduction, it's very, very rare that I hear, in fact, I've never heard the argument being that, oh, well, it's because climate engineering is going to get us out of this hole. We need to make much more progress on emissions reduction, and emissions reduction is necessary but not sufficient, in my view.
A fascinating set of ideas there from Sean Fitzgerald at the University of Cambridge's Centre for Climate Repair. So, as Mark Maslin emphasised at the start of the programme, tackling the climate crisis is actually a massive engineering challenge. But talking to our guests this week, we can see the scientists do have all kinds of interesting, ambitious and exciting irons in the fire. The threat from climate change is driving ingenuity and forcing us to develop more environmentally sound ways to exist, things that arguably we should probably have done years ago. Nevertheless, the threat remains very real. The impact that climate change will have on our lives is potentially massive, and we're also going to need social engineers to help us cope with many of the human problems that this is going to inevitably create. But that is a question for a future programme. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith, and from all of us here at the team, thank you for listening, and until next time, goodbye.